It's my pleasure to introduce Paul McMillan, who will be speaking on advanced security topics. This is a 45-minute speech.
Hello. Sorry we're getting started a little late here. My name is Paul McMillan. I work on security for the Django project, and I also work for a company called Nebula doing OpenStack work, primarily in security for the Django project. And I'm here to talk about a number of mistakes that I've seen in people's real code that have real consequences. So first, let's get started by talking about hashing and encryption. We've all seen it. Most of us use it every day. Those of you who don't must not have a computer or something. The proper application is harder than we think. Common cryptographic hashes, MD5, SHA-1, SHA-256 is the newer ones. A lot of you have probably typed these into your code. If you're typing MD5 into your code, you're probably doing it wrong. So how do we use these hash functions? Well, I get a file, I want to know whether it's been tampered with. I take the MD5 checksum of the file and I compare it with what I have. If it matches, then I've got the file I'm looking for. How else do we use this? Well, I can sign a message with these hashes. I want to use the hash to find out whether the message I'm getting is from someone that I expect it to come from. These are obvious uses of hashes. These are not obviously secure. When we are doing just a basic MD5 hash of a file, we check the hash that we have. The question is, where did we get that hash? We probably have it stored in the database. Maybe we downloaded it from the website right alongside the file we downloaded. When we do that check, if we know that the MD5 hash we have is good, we're pretty secure. It's hard to generate just on the fly another file that matches a given hash. This is not the case necessarily for all hashes, but for most hashes that are in general use, this is a reasonably hard problem. For message signing, it's a little bit different. This is a pretty common construction for someone who says, I want to check and see if this message that I sent is the same, is the message I'm expecting. Maybe we sign a cookie with some stuff in it, give it to a user, and then we want to get it back and verify that what we sent is what we got back. This is the wrong way to do it. An attacker, using what's called a length extension attack, can take your existing signed message and add some junk in the middle and then append more data onto your message. Now, maybe your application is very strict about the kinds of messages it parses, and this format will result in an error, but most often this is not the case. And if an attacker can sign messages, given one message can sign a different message, your signing is not actually done what you expect it to do. The solution to this is use HMAC. HMAC is essentially taking the hash of your secret and then appending that to the hash of your message. It's a little different than that. But what this means is that you can't extend the hash and validly compute a new message, a new authentic message. So use it like this. Don't do it the way that it looks like. And salt your secret key. If you have an application that uses HMAC in more than one place, your secret key will, these authenticated messages will be valid for any message you sign. If you don't salt it based on the use for each separate area of your application, a user may be able to take a signed message, a completely valid signed message, from one area of your application and put it into a different area of your application. This doesn't always cause problems, but if you're doing something like signing data structures, if a user can sign a message and stick it in where you're accepting a user object, that can be a serious problem. When you're choosing hashing algorithms, don't use MD5. MD5 It's not trivial to do some of the breaks on MD5, but it's definitely broken in the cryptographic sense, and you really shouldn't be using it. SHA-1 is better. It's still got the length extension problem, but it is not known to be cryptographically broken, and it's difficult to generate collisions. For now, SHA-256 is a good choice. There's also SHA-512. People ask, why don't you recommend SHA-512? The problem with SHA-512 is that on 32-bit machines, it can have serious performance problems. SHA-256 is very similarly secure, and it's not worth making your code not work well on 32-bit machines, since 32-bit machines are very common when you're virtualizing. So, encryption. What encryption algorithm should I use? What key set should I use? Should I use a block or a stream cipher? No, you should not be implementing encryption. In almost all cases, I'm right. In the 2 cases where you are cryptographers, I'm wrong, I'm sorry. The rest of you don't implement encryption. Why do you need it? You need it to protect your data in transit. Maybe you need to protect your data. Maybe you need to protect your data when you're storing it. If you're protecting your data in transit, use transport layer security. Use SSL. It's well understood. There are good libraries. Sorry? There are good libraries that exist to do this properly. If you implement your own transport layer security, there will be problems. For protecting your data at rest, use your underlying operating system. There are already good solutions for this. Writing your own so that you have some of your data in your program encrypted is just not the right way to do it. So, another common problem we have. We've got random numbers that we use all over our code. It's very common to see a construction like this. We're generating a secret key. We want something that a user can't guess. This is not the right way to do it, because the default random number generator in Python is predictable. If you take enough of the outputs, you can generate everything else that it's going to put out for the rest of the life of that process. If you're doing this to generate session keys, it means I can know the session keys of all the rest of the users who've logged into your application. The solution is use the system random import, which uses the system level random number generator, again, outside of what we're doing, and it has access to a lot more data. If you have a hardware random number generator in your machine, this will probably use it. If you have access to entropy from TCP timestamps and when packets arrive, this can use that. If you don't, people will be able to predict your random numbers. So the problem with using the system random number generator is you don't know how much entropy is actually there. In general, it's a better solution than predictable random numbers, but in some cases, this can be a real problem. For instance, if you're running your Python near the start of a virtualized machine, there's just not very much random entropy inside that machine yet. And so the system random number generator can run out of entropy. It'll still keep giving you numbers, but it will maybe giving you predictable numbers. Another common problem is timing attacks. Timing attacks are not terribly well known. So here's a common example of a timing attack. So we are HMACing a message we receive from a user. We split the signature that they sent along with the message out. We generate what we expect the signature to be, and then we compare our expected signature to the signature we actually got on the message. The problem is this. The equality comparison is not the way to do this. When we do string comparison, we do a shortcut. We don't compare every single character. We compare the first 2 characters. If they match, we go on to the next ones. And we keep doing this down the string until we either run out of characters or all of the characters match, or we find a not matching set of characters. The problem is, if you have a construction like this, the first 2 characters match, but the second two don't. It will return as soon as it finds out the first two characters don't match. Now, down below, it will return after it finds the second two characters don't match. This is an extra comparison operation, and it turns out that if you take a lot of messages, it's possible to figure out one character at a time, even a very long string like this. These are very small values. The amount of time, the difference is a very, very small value, but it turns out it's statistically decidable in, depending on your application, hundreds to millions of messages, which sounds really noisy. So it doesn't sound very practical. But especially if you're going over the internet where there's a lot of latency, a lot of jitter, these have generally been considered not to be practical ways to attack applications. Today, a lot of applications are virtualized. We're back to sharing machines, and now we don't have the network latency. If I'm on the same machine as you, I can ask you a whole bunch of questions really fast, and that makes computing these things quite a bit easier. The solution for these is to use a constant time compare function like this one. It has the property of checking to make sure they're the same length, and then it does an operation on every single set of characters, whether or not it already knows that they have differed. When you send strings like this in, they take the same amount of time to compare. So use this and think about, in your applications, think about where timing differences might matter for just discovering information you don't want publicly available. For example, it may not be easy to brute force authentication keys in your application, but it may be easy to brute force your user list. If I take a whole bunch of common usernames and try to log in with all of them, I can figure out which ones you actually have in your system so I can focus my password cracking attempts on those users rather than just trying at random. Another very common problem is improper use of pickle. In the docs, it says don't use this in ways that are insecure, but everybody does. When you load an untrusted string from a user, it's equivalent to running a val on that string. Don't do this. You wouldn't do the bottom thing there, so don't do the top thing either. If you're going to send users data and accept it back, use JSON or some other serializing format that does not operate like Pickle does. Pickle is really for internal use. It's not for things that you should be handing back and not for things you should be handing to users and getting it back. You can sign pickled data, and that is using the signing that I was discussing earlier, and that works, but it requires that you don't screw up the signing and that you don't leak your secret key. And both of these things are more common than you think they are. Don't depend on these things. Use a format that the user may be able to fiddle with the data, but at least they won't be running any Python code they want on your machine. So, we're going to talk a little bit about assumptions. When I talk to people about security, I very often hear conversations that start with, you would think that, and then fill in the blank. So, this program uses encryption. They would never do that. They would never use Pickle. They would never just arbitrarily allow users to change the values they're modifying on the server. The server would never, you would think that. No, you can't assume that. Anytime you hear yourself saying that, internally or externally, stop and say, do I know that this is true? Because very often it isn't. Much more often than you think it is. You always have to verify. So here's an example that I think is probably near and dear to many of our hearts. When I go to install a Python package, we all do this very often. Most of us use our laptops sometimes. Most of us do this over untrusted Wi-Fi networks sometimes. So when I go to do this, I generally have a bunch of assumptions. First of all, I trust the person who wrote the package. If I don't trust the person who wrote the package, then the whole business doesn't matter. And then I trust the people who are hosting the package. The cheese shop is run by a bunch of reputable people. They're not going to be slipping code into my packages unknown, and I trust them. That's a reasonable thing. And I trust the people who wrote the package manager that I'm using to install it. And all of this goes for easy install as well. I use pip, so that's what I am writing about. Easy install is exactly the same. So the other thing is we know that pip verifies the MD5 sums of packages from PyPI. We know that you can GPG sign your packages on PyPI, and we know that PyPI can use SSL. So it seems like a pretty reasonable set of things to assume. The problem is most of these are really big problems. The problem is that all of these things require you to trust everyone on the internet as a precondition because of the way pip easy install happens. If you don't know who you're talking to, you don't know that any of these other things are the case. So it turns out that pip verifies the MD5 hash that it downloads, but it downloads that hash from the same page that it downloaded the package from, and it does this in plain text. If someone can modify the package they're sending you, they can absolutely modify that hash too. Packages on PyPI can be GPG signed. Nothing checks it. You probably don't check it either. And the people who say that everyone should write down the MD5 sums of all the packages they install and then check them before they install them are in an extreme minority. And the people who actually do that are an even smaller minority. PyPI uses SSL, but not really. It uses an untrusted by default certificate. This means that for most of you, if you go to PyPI, sorry, I keep saying PyPI. I do not mean PyPI, I always mean the cheese shop. If you go to pypi.python.org, you're not using SSL, and you log in, anyone on your local network can see that password, and some of them probably have. If you go to the SSL version of this site, the certificate isn't trusted by default for your browser. You may have gone and downloaded the certificate, but most likely you just clicked through. Again, if you just click through, someone on your local network can trivially listen to what's going on when you're browsing around the site. Easy install and pip don't even bother to use the SSL. They just ask for the plain text pages, and they believe what they get back. It's not easy. The bigger problem here is that the basic Python standard library doesn't make it easy to do these things. It doesn't make it easy to do the right thing. If anybody has tried to implement certificate checking, it's hard. If you look at the code, going back to assumptions, you would think that when you URL open an HTTPS URL, you would get encryption. Well, yeah, you do get encryption, but you don't get verification. You don't actually know that the certificate that you're getting back is anything you expected. Python just doesn't do that by default. It probably should. It's a hard problem to solve, though. My recommendation for those of you that write code that goes out on the internet is to use the requests library, which is based on HTTP-lib2, and it does check by default. It's not in the standard library, but checking certificates by default is really, really, really important. So this is the point that my slides run out because I lost them, because I left them checked into a Git repo on another machine that I didn't bring with me. So this is also the point that the fabulous demos that were going to happen are problematic because they were depending on Wi-Fi. So I'm going to talk to you about what the demo code does. I don't believe that I am going to be able to demonstrate it to you. And so when your computer, when pip says, I want to install a package, it goes to pypi.python.org/simple, asks for the package name, and gets back a result. Before it can do that, it has to do a DNS lookup for where pypi.python.org lives. DNS lookups are UDP. You send out a packet, and you wait for something to come back. It takes a little while to go all the way out to the internet and come back. Since I'm sitting in the same room as you, it's very easy for me to generate the response and give it to you right away. Your computer will get back 2 responses, but it just trusts the first one by default. This means that I can tell you that pypi.python.org lives anywhere I want. So I set up an example of that. And so this machine believes that pypi.python.org lives somewhere that it doesn't actually. Let's see. Doesn't. So maybe you do that sometimes. If you're doing that, then you're letting other people run code as root on your machine. And what happens in this alternate world is that the packaging index looks at the file you're asking for, opens it up, modifies the setup.py a little tiny bit, and serves it right down. You go ahead and install it. If the demo had worked, any of you in the room could have typed pip install whatever and would have gotten the same result. This is a problem. We treat the Python package index like we treat the apt repos. We treat them as trusted, we treat them as secure, and we use them all the time. We use them all the time in places that we don't necessarily absolutely trust our internet connection from one end to the other. We have to stop doing this. We need to implement package management tools that take advantage of these security techniques. PyPI offers almost everything to make this impossible. Right now, but we don't use it. It has an SSL certificate. It has an SSL certificate that's untrusted by default, but we could pin the packaging tools to that. It has GPG keys. We could make those check them. Just checking the MD5 of the package is not enough to tell us that what we're asking for is what we're getting. What else would I have to talk about? So my question for you is, how do we help the Python community get to the point where doing this kind of thing just isn't something that accidentally happens? We all know that it's hard to do security right, but we really need to make the choice to make it easier for everyone in the Python community to do it right. A friend of mine is working on a project called crate.io, which is a mirror of PyPI that has some more of these features. That's one thing we should do. If you're writing software that talks to the internet, consider using the requests library because it's saner to use and it checks certificates by default. If you're writing hashing algorithms, things that use hashes, use HMAC. And use HMAC of the message you really mean. Amazon had a problem where they had message signing algorithms that were good, but the problem was in order to generate the canonical message, you had to modify the inside a little bit. And that turned out to allow you to sign arbitrary things that were different from what you were expecting. Anyway, that's what I've got. I'm sorry the demos didn't work. So, questions?
And we have a mic over here, so if you have a question, please approach the mic.
Hi, Paul.
Hello.
So, as you may or may not be aware, I occasionally release Python packages into the wild.
Whoa.
And there's a process that I go through for this, where I make the package, using setup.py, and get MD5 and SHA-1 checksums of the package, put it up on the cheese shop, put up a file elsewhere on a server I control, with a list of what those checksums are, and that file is, GPG signed. There's nothing that checks this. We encourage people to check it. Do you think, and we can continue this conversation in detail as much as you like, do you think there's a better way to do this from the release process? Are there things we can be doing that, even though like pip and easy install and the tools aren't necessarily doing the automatic checking, are there things we as package authors can do right now until the tools catch up to help our users be more secure and know that they are getting the packages we actually made?
It's a hard problem. If you put something in the package that verifies that the package itself is what you expected, someone who can modify the package can modify that tool.
Yeah.
If you provide something alongside the package, it's the same problem. The way they got the package and the way they get the tool to verify the package means that someone who can modify the package can modify the verifier.
Yeah.
In the case of the signed GPG files, it's great, but almost nobody checks this.
Nobody checks this. The only person who checks the Django GPG signed files are Alex Gaynor, and that's only because I ask him to when I'm rolling a release.
So we need to make the tools do this automatically.
Okay.
No, what you have to do is make it harder for an attacker. If, I have a series of keys that have been used to sign a release over the course of the last couple of years, the release has been fine the last couple of years, then it's probably pretty reasonable to assume that the release is going to continue to be fine if it's signed by those keys. If the release isn't signed at all, well, I hope I trust all of you.
So I've got a marvelous question because I think it works regardless of what the speaker actually talked about.
Excellent.
And the question is, how much of this is actually new? And I'm going to give you two variants of this question. The one of them is, how much of this is actually new? And the other question is, how much of this is actually security specific? Because if you take the pure software engineering perspective, everything you said about HMAC and a lot of these system routines, what you're really saying is, don't reinvent the wheel. And then there's a subtext of, because it has security consequences.
Absolutely.
So the question is, are there actually cases where the only reason you have to do something is because of security? Or could every single one of these things come under fundamental engineering? You know what, it's 2012, not 1979. Every wheel that you could think of has been invented. If you ever find yourself actually writing lines of software, you probably shouldn't have done so. You should have treated it as an engineering job and used the pre-existing code. And then the other half of it is how much of this is new, because even taking examples from your talk, the pip install thing, Perl went through this with CPAN, the hash collisions thing that I believe you were going to talk about, the Linux kernel went through it, Perl went through it, Java went through it, the SSL verification, Java went through it. This really isn't new. Should there not be some survey to sort of bring Python up to date? So I'm afraid that's two questions. You're going to have to disentangle them. Thank you.
So the first about, is this new? No, none of this is new. But this is stuff that we pretend doesn't exist. As a community, we say, it's not my problem, don't talk to me about that, I don't want to hear it. If you look at the messages on, I do not encourage you to read catalog sig because it will make your blood unhappy in your body and it will maybe leave. If you do read catalog sig, you will see that the broad, the end result of most conversations about this are, it's not PI's problem that users are doing something insecure, they should be doing the right thing. That doesn't work. Users don't do security by default. You have to make it so that the thing that is obvious is the thing that's secure.
But in almost every one of your practical examples, doing the insecure thing was more work than doing the secure thing. It was more lines of code. It was more effort than doing the secure thing. So what this really comes down to is just bad engineering on the part of users who people as a theme know how to program, and therefore they think that writing code is the answer to the question.
I agree that using higher level constructs where appropriate, where they're available, tends to help make your code more secure. Part of the problem is recognizing where you have to use those constructs.
You said you couldn't do the demo because some issues with the Wi-Fi. Is that due to security features on the Wi-Fi routers that we're using here?
Actually, the script that I had was set up to do the attack over a WPA2 encrypted network, and this is an open network, and my code made some assumptions.
So one counterexample of the higher level construct is better, or a great example of something you would only ever do for security purposes is the timing attack example you gave. Who would ever use that convoluted a code to check two strings, except that if you don't, if you use the easy, good software engineering equals, you're screwed.
Yep.
So I'm surprised you
have
didn't
to-
answer this
you-
to that.
Yeah, you have to think about the security implications for all the pieces of code, and the answer is different depending on what your problem is. How much time do we have left?
If you use the libraries to begin with, they will use the proper equal.
You would think. That's the way it should be.
Almost no one in this room should ever have to worry about a timing attack
Yes.
in terms of implementing. You should be using higher level libraries that worry about it.
Python should have a constant time compare function. It doesn't. Yeah? Yeah. So if we, go ahead.
So about the constant.
Yeah.
About the constant time comparison function that you posted, CPython interns integers in a certain range, and so that means that you'll end up with mallocs or not mallocs, depending on the inputs you gave. So it would be challenging to tease out, but I think that you could probably mount a timing attack against that version too. I've looked into this a little bit. There was a talk at PyCon last year that covered timing attacks, and I don't think it's possible to implement constant time string comparison in Python.
What's possible is to do something which is very, very, very close to it. It's a lot better than the equality.
You can
and
make
at some
the
point
attack
good
harder.
enough. Yeah.
Yeah.
I mean, I don't think it's possible to write it in C either if you get really, 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 really all the way down to the middle. But
So the pip vulnerabilities that you displayed are concerning, and my understanding is there are a lot of people who work on big Python installations and distribute and deploy a lot of big Python apps on lots of servers. So I'm wondering if you know of any examples of hardened, Python package distribution things in the wild, or if you have any suggestions for the trenches.
for most large software projects, you have some system for finalizing your packages that you roll out to the servers. It's unusual in a really big installation environment to have something actually installing packages from the cheese shop. If it's doing so, it's checking the MD5 sums that it already has, and that makes it harder to attack your servers. I believe that the pip people are going to be sprinting on getting authentication into it. Hopefully by the end of the weekend, end of the sprints at least, it will have that. The problem is if you have, unless you actually are keeping copies of the package yourself, you need something more than the MD5 sums that PyPI offers you. Because it's possible to do things like generate two packages with the same signature, upload a good one to PyPI, and then serve a malicious one sometimes if you're attacking someone. Then everybody says, oh, I trust the package on PyPI, look, it's good, except that you get one with the same MD5 that's not good. Subtle attacks are less likely, but they're certainly possible, and we should use things like SHA-256 checksums and GPG signing to make that not easy.
So I think at some point you mentioned, was it crate.io that was trying to make a hardened package index? Mm-hmm. Is that accurate?
Yeah.
Presumably you're going to be using the same client tools, pip and easy install, to access that? Yes. Yeah. So what does that do to increase security if the installers are still the same?
It's mostly a bunch of things that are obvious that that PyPI hasn't implemented. Things like storing the SHA-256 hashes of the files, storing the hashes long-term so you have a history of what files were there. Right now, pip allows you to pull a file down, delete it, upload something with exactly the same name. You as a person who's using it can't tell that that's happened. So you check the package, and then 2 minutes later you pip install it, and it's a different package. That's a problem in my book. And it will, Crate is going to maintain a history of the packages, so deleted packages don't go away. So, someone uploads a malicious package and then they correct it later and claim there was nothing there. You'll be able to see that. It's also better with the SSL. It doesn't serve the standard stuff over unencrypted links. It's a whole bunch of small things.
Setup tools and distribute allow requirements for a package to be obtained from a different package index through the dependency links option. So no matter how secure you make PI, if a package gets its dependencies from some untrusted source,
if you're running,
what do you do?
If you're running the pip, if you're running the install tools in an environment where you care about security, you don't do that. You just cannot spider external links that way. There's no way to verify that the external links you're spidering are what you're looking for, even if you include, a list of root certs that you trust, and then, you SSL verify where that link went to. It's an unsolvable problem.
Right.
If you care about security, the packages need to be hosted in the same place, which has the same level of security for all the packages.
I've worked in places where we care enough that we don't care how secure the source of the packages was, because we're going to look at their contents anyways once we get them. So
absolutely,
maybe there's no point to any of this.
Except that everyone actually uses it this way. So practically speaking, it matters. Because maybe you audited what went on in your server. Did you audit every single package the developers ever installed on their dev machines before they installed it?
Probably not.
Exactly. Any other questions? All right then. Thank you.